Great. Okay. So today I'm going to talk to you guys about potentiostatic electrochemical impedance spectroscopy, which I will interchangeably call EIS or impedance, like taking impedance or whatever, analyzing impedance, and I'll use them interchangeably throughout. I have potentiostatic here in parentheses because there's also galvanostatic electrochemical impedance spectroscopy, which has the same roots. If you can guess, based on etymology or roots of the word, galvanostatic has to do with varying the current a tiny bit, and then potentiostatic is where you vary the potential a little bit. But we'll get into the details of that as we go. So just a quick outline of my talk. First, I'm going to talk to you about some uses of EIS and introduce it a bit. Then we'll talk about imaginary numbers just as a refresher, some of the basics that will go into that. Representations, meaning what types of plots we use for impedance. Fourth, we will talk about equivalent circuit models that are used in analyzing impedance spectra. And then finally, I will bring you through some examples and talk about some practical considerations, which are pretty important when you are choosing to use EIS with your system. Before we get into that, I want to briefly touch upon some sources. So throughout, I will be using stuff from Electrochemical Impedance Spectroscopy. This is something that I think both Jeff and Will and Eddie all recommended to me at one point or another. Also, Martin Bazant's online MIT OpenCourseware Electrochemical Energy Systems course notes, very useful. And of course, the most important is Mary Louise' thesis, electrocatalysis in solid acid fuel cells. And I'm going to use them throughout. I'll note if there's something in particular that came from a particular source that's like maybe more copied than other things. But I'm not going to reference them with superscripts throughout. And then I just wanted to show everyone how many times I've made Jeff and Eddie send me these different sources and just forgotten, with EIS resources at the very top being the most recent one in the last 2 weeks. So I've always had these resources, but maybe not delved into them as I should. All right, let's get into some uses. So most broadly, essentially, I'll just delete this for now. It enables us to investigate interfaces and processes that are occurring when they're stimulated by an electric field. Although the way I like to say it is thinking about what's actually going on. So essentially what you do in potentiostatic EIS is you're wiggling potential, so you're wiggling V, and then you're going to watch what happens with the current. And then from that, you get impedance. And we'll get a little bit into what impedance means in a bit. Before that, I'm going to tell you about some examples. So you can determine the extent of corrosion on stainless steels over time using EIS. You can detect binding events on biosensors. Don't know exactly how those work, but I've been told that is something you can do with EIS. You can understand charge transport in fuel cells. And then finally, you can calculate solid electrolyte ionic conductivity in solid state batteries. And these are just very small examples. People in our group use it for all different it basically holds a constant potential. And then it creates this sinusoidal perturbation in your potential. So make sure I have my actual notes up. So what we're doing is essentially creating this potential that comes in as VO times the exponent of j omega t. Now this j is an imaginary number. Sometimes people will use I, and again, we'll go through imaginary numbers a bit. And then basically you want to measure the current response. And then the current response is given as some sort of constant initial I times the exponent of j omega t, the same function out, but you're going to have some sort of phase shift, which is represented by phi. And this expression is true for small signals in a linear current potential regime. And so what this looks like, if we're going to draw it, is your potential is essentially going to have this nice, sinusoidal looking thing. This is so much harder to draw in situ. And then out of it, we're going to essentially have this, you know, phase shifted, oh, let's see if I can do this, current response. And so to label some of the important things on this axis, essentially this guy here is going to be your VO, this is going to be your IO, and then this shift is your phase shift. And then what you get is your impedance. And you get impedance just by dividing the current or the voltage by the current. And if you're like me, you immediately think of Ohm's law. So like V equals IR. So dividing the two will give you resistance. And that is only true when you are actually dealing with a resistor. And there are a couple different circuit elements that will respond in different ways. And you can basically predict current coming out of it in different ways from your potential. And so continuing to kind of analyze this and get this down into a form that's typically used to analyze impedance, I'm just going to simplify a bit. So this simplifies down to VO over IO times the exponent of negative J phi. And then we call that the magnitude of the impedance, Z, times the exponent of negative J phi. And then here I'm using Euler's formula, which again we'll review in a minute, to just break that exponent down so that we get, it's the magnitude of the impedance times the cosine of phi minus J times sine of phi. And here I've labeled it ZR and ZI, corresponding to the real and imaginary parts of the impedance. And we'll go through this again just to make sure it's actually sticking with everyone. And the last thing I'll say is that this is often also described as the complex frequency dependent response to an AC signal. It's another definition for impedance. All right, so now let's refresh you on some imaginary number stuff. So first and foremost, J, sometimes I, is our imaginary number in this case, which is just equal to the square root of -1. And so thereby J squared is just equal to -1. If we want to write a complex number, which has a part that is real and a part that is imaginary, we usually do it in this form. Again, the real part on the left, the imaginary part on the right. And just to drill that home, the x sub r is the real component, and the x sub I is the imaginary component. This is also written as basically RE with curly brackets. X sub is the same thing as x sub r or MZ. And so you'll see all these representations. Another important term to remember is a complex conjugate, and that is essentially, we represent that here with an x bar, and that is essentially your original complex number, but you just have a negative sign here, so you change the sign of the imaginary part. Next, another important thing to remember is Euler's formula, and I have a note here. I did some historical digging on every person kind of mentioned in my talk today. I didn't know that E was created by Euler, and I'm guessing that's where the E comes from. I know I would use E if I were Euler. And that he also was the one who ascribed pi to mean, 3.14, etc. The other interesting thing I found about Euler is that he started to go blind in one eye, and he's quoted as saying, after I think one of his contemporaries called him a cyclops, which is rude and don't do that. He said, that's okay, now I have fewer distractions. So that is a true scientist there. So basically Euler's formula is just saying for an exponent of some sort of imaginary number times your variable, you can expand that to be the cosine of that variable plus, and I'm saying minus here because we have a minus in the parentheses in this case, the imaginary number j times sine of phi. And so then again, your real part is going to be the cosine of phi, and the imaginary part is sine of phi. And that's just where we got the expression from before. And then the final thing that'll be important as we go forward in analyzing some of our data is knowing how to find the magnitude of a complex number. And so for a vector, as a simple type of example, think of your 3, 4, 5 triangle. we find the magnitude, or the hypotenuse, if you will, by taking the square root of each component squared. So 3 squared plus 4, ooh, that's cubed. This is just equal to 5. And so if we want to do the same thing with our imaginary numbers, again, you take the real component and the imaginary component. So you take the square root of zr squared plus, then you have j squared and negative zi squared. And this, after doing the algebra, will come out to be the square root of zr squared plus zi squared. So this is how you find the magnitude of your imaginary numbers, or of your, what's it called? Your impedance. All right, now that we have, this basis down, we can get into actually looking at how we interpret our data. So the two plots I want to talk about are the Nyquist plot and the Bode plot, sometimes called Bode Plot. A couple notes about Bodhi. I couldn't find too much on Nyquist, but Bodhi, aside from, doing this, advanced type of math, also created robot weapons, as Wikipedia says. I'm quoting directly, which is not great. So I like to think, instead of the alpine skier Bode Miller, and I spent quite a while drawing this because it's the best way to make presentations. And basically out east, there are a lot of trails named after Bode Miller that I grew up skiing on. So I'm going to pretend that he also went on to create these lovely plots. But let's start with the Nyquist plot. So a Nyquist plot is essentially a complex conjugate of your impedance, but plotted component-wise. And so if we're, going back, we remember our complex conjugate is just going to be ZR minus J Zi. And so we're plotting essentially the minus Zi portion instead of plus Zi. So what we do is we essentially vary the frequency at which we're oscillating the potential. And then we take different points of impedance based on the current and voltage response, or the current response to the voltage wiggles, if you will. And so again, on the y-axis, you have your imaginary impedance. On the x-axis, you have the real impedance. And I'm showing you a random example here. We do very often see these semicircles, and we will get into it in a little bit, why we exactly see those semicircles. There are other shapes that can form. This is just one example. And so essentially what we do is we plot the different frequencies here and see what shapes emerge, connecting them by increasing frequency. Then we go to the Bode plot, another useful one, but I will spend most of the time today talking about the Nyquist plots. But this is essentially you plotting phi, so the phase angle, and the magnitude of z. Remember, we talked about the magnitude before, as a function of omega, your frequency. And so I say here, recall that, the magnitude of z can be found with this formula, as we already derived. And then you can find phi as given by the inverse tangent, just solving the, v over I formula, etc., of the imaginary number, or imaginary impedance over the real impedance. And so what this ends up looking like is essentially for, your magnitude of the impedance in blue and the phase angle in yellow, these various curves where inflection points tend to mean a lot. And we can go through Bode plots in a different time, but for now I'm going to stick to understanding things through Nyquist plots. So we know how to do these representations. We know how to take the data. You just vary your potential. You wiggle that at different potentials, different frequencies, and then you figure out what the impedance response is. So how do we actually analyze what comes out? Well, essentially what we want to do is understand, in a certain way, how we can model our system to predict these different shapes and features. And to do that, we tend to build equivalent circuits. And so just maybe to go through a refresher on things and derive how we get impedance for these different equivalent circuits, I'm going to go through some of the more basic elements or common elements that are used. So first, a reminder that impedance is the potential over current. And we know there's a couple classic elements that actually fit with observations very often. So resistors, inductors, and capacitors often fit what's happening physically in a system and can be, rationally tied to what's going on. So these are the common symbols used to represent resistors, inductors, and capacitors. I spent quite some time trying to create this shape because you don't have the lovely straight line feature that you can use. So first, starting on the left with resistors. What we can say here is that, the potential is equal to the current times the resistance. Again, Ohm's law. So if we're going to divide our, as we have up here, our potential by our current, then we just end up with impedance equaling R. Cool, we can handle that. Next, on to the inductor. The inductor is very often described as the potential is equal to the inductance, L, times the time derivative of current. And so just as a reminder, our potential is given by VO exp of j omega t. And our current, we found before, is equal to IO times the exponent of j omega t, what was fit, times j phi, a little bit over the box there, that's okay. So then the time derivative here is going to give us j omega times I of t. So just times itself, as is the rule for different exponents. And so in this case, we end up with an impedance after, a little bit of math that is equal to j omega L. So now we have a frequency dependent impedance. Makes sense. Finally, we have the capacitor. So a capacitor is described by the equation C, the capacitance, is equal to the potential derivative of the charge transferred, Q. That's how I write Q, these guys. And I would like you to recall that current is equal to the time derivative of Q. So again, after some algebra, you find that the current is equal to the capacitance times the time derivative of potential. And you find that the time derivative of potential after from what we have as our original expression for potential is again just equal to j omega times the original expression for potential. And so finally, you end up with an impedance for a capacitor as equal to the inverse of j omega c. So these are some of the standard capacitances, standard impedances that we find for these classical elements. And we'll see in a bit how these actually look when you apply them to different circuits and what shapes they may take. But before that, I want to talk about elements based on physical models. And so when I say this, I'm saying, okay, we don't necessarily have something from our classical circuit analysis that applies, but we know what's going on in a system. So maybe based on a physical process, we can create a new element from that. And so the example that a lot of people use is the Warburg impedance. And so I'll use that as an example. It is basically when you have rate limiting diffusion. So for example, if some, electrochemical reaction is limited by a reactant actually diffusing and getting to where it can react, then you're going to use this you're going to expect this Warburg impedance. So for this, we start with Fick's second law to describe diffusion, and that is going to be the time derivative of concentration is equal to the diffusion constant times the second spatial derivative of concentration. And so what we do here is we essentially analyze different boundary conditions and take limits in different ways as a way to understand what this feature might eventually look like. I will say first that Fick was able to actually double publish his theories of diffusion in 2 separate journals because they applied in 2 very different fields, I think one of them being medical and I forgot what the other one was. But he was also a prospector, I think that's what it's called, which is essentially someone who dissects human cadavers. And he was the first person to actually measure cardiac output. Wow, I know very little about biology, but just shows you how Kinetics is everywhere. Anyways, so after applying those boundary conditions and figuring out in different limits what happens, we're able to come up with 3 commonly used versions of the Warburg impedance. So first, what you get if you have an infinite length over which your reactant is diffusing, you come out, I'm not going to go through the exact derivation. It took several pages in the first book I referenced, the Orzem and Triboulet book. I think that's how you say the name. It's definitely French. The guy is French. Anyways, so this first one, if you do the actual derivation, then plot it out, essentially the imaginary versus the real impedance looks like this 45-degree line. And essentially you have this little like raised to the n factor, and depending on what n is, that will vary this degreeage. I think if it's 0.5, then you do get a 45-degree angle. I'm sure one of you can check my math on that though. Then we have another example. Say you have a finite length, so shorter, and you have fast supply of the reactant. Then what you have is essentially like a 45-degree line leading up to an expected arc, and we'll talk a little bit again in the future about how you get these semicircle arcs. And then finally, we have, if you have a blocked slow supply of reactant, finite length, then you get essentially what looks like the start of a 45-degree line, then it just, goes straight up. And so basically, as you're looking at your system, you can use these as a way to understand what's happening diffusionally in your system and whether that's the most prevalent thing going on. So next question for me would be, okay, so how do I actually use these circuit elements to understand what's going on in my system? And as you might expect, it's okay if you did not, the best way to understand this is if you can combine them using, an equivalent circuit model. I come from chemical engineering as a background, and we use equivalent circuits in that field to understand, different resistance to fluid flow through pipes. I spent a lot of time thinking about pipes in my undergrad. So we're going to think about, instead of fluid flow, we're thinking about, or electron flow, we're thinking about like lithium ion flow in a solid state battery, for example, and how we can model its different paths, where it's going to stick around, where it's going to flow a lot better using an equivalent circuit model. And so again, say we have some plot. This maybe is a plot you might see if you do impedance on your system. The most important thing to start off with is remembering Kirchoff's laws. Might be Kirchoff, don't know. Should have looked that up ahead of time. But I'm going to show you a slightly different version of what you might expect. Usually these laws will help you understand what happens in parallel and series in circuits in terms of resistance and current and potential. But what I have for you here instead is impedance and admittance. Admittance should be a new word for you. So impedance is what we've been talking about. It's our Z. And in parallel, you're going to essentially add the inverses of each of the impedance elements that are in parallel with one another. Yep, sure. And then you take the inverse of that. And then in series, you just add them. And then admittance is just the inverse of impedance. So it's just something that represents the inverse. It's useful in other scenarios. And again, then you just get the inverse relations for parallel and series. And then I wanted to note that Kirchoff and or Kirchoff also discovered cesium and rubidium, if anybody cares. Continuing on. So what I'm going to do now for you is essentially bring you through some of the, sorry, I don't have chat up. Cool. I'm going to bring you through some of the common or some equivalent circuit models that are maybe used more often than others as a way for you to get familiarity. So I would say the most common one, and the one that actually creates the semicircles here, is the RC circuit. I know I've been alluding to it the whole time, so let's finally get there. So the RC circuit is essentially a resistor and a capacitor in series. And recall, a resistor's impedance is just R, and a capacitor's impedance is J omega C to the -1. And so for calculating the impedance here, we're going to say, okay, these two things are in parallel, and according to Kirchoff's laws, we have that it's going to be the sum of the inverse of the sum of their inverses impedance. So that is going to be 1 over R plus J omega C. all to the -1. A little bit more algebra. We want to essentially get this in a form so we can separate it into an imaginary part and a real part. So flipping this bad boy around, we have 1 plus rj omega c over r all to the -1. And then actually taking the inverse of that, r over 1 plus r omega j c. Yep. And then what I'm going to do is just multiply by 1 minus r omega j c on both. And that will give us our final expression, which has a real and imaginary part of r over 1 plus omega squared r squared c squared minus j times omega r squared c all over 1 plus omega squared r squared c squared. Riveting, I know. And so when you plot that out over various frequencies for a constant, resistance and capacitance, what you get is this lovely semicircle shape. And let's just talk for a second about, how you might actually get like an RC circuit. And so if you imagine an interface that maybe starts to charge, so a capacitor is going to be an interface that starts to charge a bit, and so some charge is going to go into charging that interface, and then eventually it'll reach its full capacity, and then it's going to start passing it through like a resistor, and so then there's going to be some resistance to it. And that is essentially, if things weren't happening instantaneously, what the RC circuit actually represents. And so I want to go into some of the key characteristics of these semicircles that you want to know when analyzing your data. So first, looking right here, when you have the imaginary part as 0, so it's all real, and omega goes to 0, meaning your frequency is so small that you're essentially doing DC potentiometry rather than AC. If you want to simplify your equation, you end up finding that your impedance is just equal to R. So again, you have like a resistor. And so if you go all the way to this point at the end, where your imaginary impedance is 0, this basically is equal to R, the full length of your curve. And so, did I do that right? I'll have to check that math. For some reason, I thought it was R over 2. Continuing on, assuming that's right. And so, right. And so then the next thing that's important to actually look at is the characteristic frequency of an arc. And so I'm going to denote that as omega sub O, and that's just equal to 1 over the time constant, characteristic time constant, which is, tau, which is 1 over RC, so the resistance times the capacitance. And so I want to know, when do we actually get this characteristic frequency for the arc? So plugging that into our formula for impedance, if we look at the real portion, so the real portion represented here, and the imaginary portion represented here. For the real portion, if we plug that in, we get that is equal to, as we had before, R over 1 plus omega squared c squared r squared is equal to R over 2. Yeah, I definitely did my math right. Have to not doubt myself. And then for the imaginary part, again, we had this is equal to omega r squared c over 1 plus omega squared r squared c squared. And this, again, is equal to R over 2. So essentially, we get our characteristic frequency when ZR is equal to negative ZI, or when Z is equal to 0. And so that actually occurs at exactly this point. So in this case, we have exactly R over 2 and R over 2. And at this point, basically the crest of every semicircle that you have, that is going to be where your characteristic frequency is. So if you're going through looking at your data, you have a semicircle, the characteristic frequency of that arc is going to be the apex of it. And that's going to be important later on, as you will see. All right, so back to this data. What is its equivalent circuit? Now that we've kind of seen like how RC fits into this. So you can kind of envision this is going to be one RC circuit. This is going to be another RC circuit. somehow they're shifted up like this. So if I had to imagine how to actually note this, I would say, okay, there's some sort of offset here that is represented by, let's just say this is R1. And then we have another semicircle of radius R2 or resistance R2, and then a third feature R3. And this has our characteristic frequency omega O2, and this one has a characteristic frequency of omega O3. The first one's not a semicircle, so it doesn't really have one. And so if I were to make an equivalent circuit, it would be some sort of resistor in series with two RC circuits. And again, these capacitances are determined by, your characteristic frequency. You can just back calculate those. And so because we know that impedances are additive, this is just going to add to this, this, and this, and that's why they appear one next to each other. Okay, that was a maybe fairly simple-ish example. It's okay if I've lost you somewhere. But I'm going to go through maybe some trickier ones now, or other things to consider that you might see in your data. So on to our examples and considerations. So what happens when we have inductance? We've talked about resistors, we've talked about capacitors. I've conveniently left out inductors. And the reason I did that is because at least in my case, I never want inductance in my system. It usually means something is kind of set up wrong. So usually an inductor, I'm going to give you an example here where I have an inductor in series with an RC circuit. And what this ends up looking like is essentially this curve starts to go negative. And so basically anytime I see a negative thing in my spectrum, I'm pretty sure that there's some sort of inductance. And inductance very often comes, from your wire leads not being positioned correctly or being too long. So those are some practical considerations for you if you're starting to see some negative portions of your spectra. There's also some other potential causes, but that's very often it. And I just have a little note here. I have pictures of Tyler and Chiyoung because I still remember that first summer I was here, dragging both of them individually into the lab and making them interpret my impedance data and tell me what was wrong. Eddie as well, I think. When you don't know how to analyze your data or what's going wrong, there's many people in the lab who will likely understand it and will be glad to at least think about it with you. I know that's not the lesson you thought you'd be getting today, but here I am dishing out life lessons. Okay, then I want to talk about the RQ circuit. So I don't frequently use this to fit my data. I try to stick with RC circuits, but this is something that was highlighted in Mary Louise' thesis, so I figured I'd touch upon it as well. And so instead of this resistor here in parallel with a conductor or a capacitor, what we have here is something called Q. Oops, not duplicate, delete. And essentially what it is just the capacitance raised to some value, the j omega raised to some value n. And what this allows you to do is it accounts for semicircles that are not, perfect semicircles as you might expect here. Instead, you have one whose center is slightly shifted below the x-axis. And so this is an experimentally observed element that we use, but it's kind of non-physical. People aren't entirely sure where it comes from. So it's something you can use to fit the data, but if you can't really interpret it, it maybe isn't as much use to you in understanding what's actually going on in your system. And so this is one thing you can use, but you should try to think more practically about what's going on in your system and how to fit it. And then on to my last topic, I just want to give you some words of caution on fitting real data. So this is my data. We basically have, going from high to low frequency, left to right in my spectra, as I've detailed for you here. And there's a bunch of different features here. So you've got this like small semicircle when I'm in my pristine state. So when I make a solid state battery and haven't charged it or anything yet, I get this and then this thing, unbeknownst to me. I'm still trying to figure out what that is. And then when I actually charge it, I get this spectrum, this lighter yellow. I understand they're very close in color, and I did that to torture you. It does actually have this original arc attached to it. It just doesn't show that because I'm using the BCS for that, and it doesn't have that high of a frequency range, unfortunately. But just imagine the light yellow also has this lovely curve here. And so I'm identifying here for you about 4 features. So 1, 2 is this weird line thing, 3 is this other weird line thing, 4 is this giant arc here. And I'm looking at this and I think, okay, what do I have here? And so, you know, just from the start, I'd be like, okay, maybe I have like, you know, an RC circuit and a Warburg impedance, and then maybe an RC circuit, another RC circuit, and then a third RC circuit. But this could be a whole bunch of things. So let's get into how we actually do that. And just so that everyone understands the makeup of my cells that we're looking at here, I essentially, for my anode, use indium metal that alloys with lithium. That's not something you need to remember. It's just what I use for my anode. Then we have the solid electrolyte in the middle, and then we have the composite cathode on the other side. And for some reason, there we go. Composite cathode on the other side. So we've got interfaces here, and I told you interfaces are what we're probing, right? And so we've got interfaces between the cathode particles and the solid electrolyte. We've got interface between indium and solid electrolyte. We have, you know, resistance to lithium ion transfer all the way throughout here. So these are all things I'm considering when I'm saying, what is going on in my system? So how do we fit these features? Well-defined system and experience. Experience is super important because you can easily trick yourself into thinking you're seeing something. And it's very important for you to understand, you know, the shape of your system, the different interfaces, because if you're going to try to model it, you don't want to model it, you know, as a planar system when you've got some sort of composite like I do, or things along that line. So let's start with analyzing our features. So feature 1, again, it's going to be this arc at the beginning. What could that be? So literature, this is experience, this is me getting other people's experience, tells me that this is the bulk arc, meaning this is the resistance to ion transfer that exists in the bulk. And that comes from the idea that at high frequencies, you're actually probing only a small region. And so this is where I'm taking a schematic directly from Mary Louise thesis, and I do not want to take any sort of credit for it. So what I have here, I added in some grain boundaries just for effect. So let's use blue. Okay, so at a high frequency, you can imagine that we're only going to traverse a really small distance, and so we're within even 1 grain. So we're really probing what's going on in terms of ionic conductivity in our solid electrolyte. Then if we increase our frequency a bit, we start to pass through some grain boundaries. So this is our mid-frequency range. And so we pass through grain boundaries and we can start to probe those interfaces, grain to grain interfaces. So you might see, you know, an RC circuit from that. And then finally, once we're at the very low frequencies, all of a sudden now we can account for the fact that we're going all the way into maybe an electrode, whether it's here or it's this electrode. So once you get down to lower frequencies, you can, you know, pass your lithium ions a little further, and therefore you can probe larger areas. So I'm pretty comfortable saying this is probably the bulk arc. We will go into how I made sure it was the bulk arc in just a bit. So then we come to our other 3 features, 2, 3, and 4. Okay, this could, if we go back to 2, this could be a giant RC circuit, right? This could be an RQ circuit, that kind of non-physical circuit I talked about before. This could also be a Warburg impedance. But what is it from? I'm kind of left without some answers here. I can model it, but that's not telling me what's it from and how I reduce it. The third feature, that kind of appears after we charge. So going from this dark yellow line to the bright yellow line, we see this one start to form. And then the other thing that happens when we, you know, charge it, I can actually see the evolution of this becoming arc number 4. So I can pretty much say, and go back to feature 2, I think this is an RC circuit that's just changing resistance. So I can go back here and say this is my RC circuit. But 3, I'm still left with the, is this an RC, an RQ, or a Warburg? And then the last one, it's likely the RC circuit that it becomes. That comes from feature 2. But again, what does this come from? And I've done some experiments to, figure that out. I'm fairly certain feature 2/4 comes from the composite cathode changing in lithium ion conductivity and electronic conductivity as you charge and discharge it. I'm pretty sure feature 3 is either from the indium solid electrolyte interface or from a resistive layer that forms. But what I'm going to talk about is how I made sure that number 1 was the bulk arc. So what I did is I did a varied electrolyte impedance study. So if you look to the right-hand side here, how am I doing on time? It's always 9:41 here. Okay, 9 minutes, I got this. What I did is I changed the thickness of my solid electrolyte. And the idea here is that changing the thickness will just change the length through which lithium ions pass. And therefore you're gonna have a larger resistance, and it should increase linearly. So as I double thickness, for example, I should double resistance without changing the characteristic frequency. So what happened is, if you're looking at my plots here, this is from a group meeting back in February, I think. These are different spectra. You can see that this is the bulk arc, all of my 0.5 millimeter thickness. Then I did it again for a bunch of 1 millimeter thicknesses, and then again for 2 millimeter thicknesses. And what I saw is, okay, as I increase the thickness, I do increase resistance. So it's probably the bulk arc. But what I did find is that doubling the thickness less than doubled the resistance. So this line does not have like a slope of 1. And then also the characteristic frequency changed with thickness. So I made sure to actually analyze the characteristic frequency as I went, and you can see it started to change a bit. And so that to me means, okay, this can't just be one feature, because if it were one feature, you would have the same characteristic frequency no matter what. As the resistance changes, the capacitance changes accordingly. And so to me, this means very likely that giant bulk arc is likely made up of more than one RC circuit. So there's likely something tucked in there that's just totally dwarfed by the bulk arc that I am convoluting with it. So yes, part of it is going to be the bulk arc, but there's likely another arc in there or some other feature that I am not modeling correctly. So this is just kind of a lesson to say, you might think you know what's going on in your system, even when you see this lovely bulk arc that you were expecting and everyone in literature tells you to expect. You have to think about it carefully and experiment carefully to make sure what you're probing is, or what you're assigning something an equivalent circuit is actually correct. So with that, I am going to actually end my talk. The main outcome being just be very careful when you're using impedance. And I want to say thank you for listening. I also spent quite a while on this. The last thing I just want to say, I know I highlighted a bunch of, old white dudes in this talk, so I just want to highlight one old white woman. This is Edith Clark. She worked at GE. And she developed both the Clark transformation, which is a mathematical concept, as well as the Clark calculator, which is for power transmission lines. She was the first woman in the American Institute of Electrical Engineers, first one in Tau Beta Pi, and the first female professor of electrical engineering. And then also did circuit analysis of AC power systems, a book based on her notes from GE. I've looked for a lot of other, people of color, engineers, and found very little, though that definitely warrants a little bit more looking. Last thing, this is my sister's dog who has my heart. His name is Cooper, and he's both perfect, infallible, and flawless. Thanks.
Thanks so much, Emma, for that excellent tutorial. I really like the way you present. It's very unique, and I really like it. Good job. That's something to learn from you, I guess. I think Alan and Gabe has some discussion or comment in the chat. Alan and Gabe, do you want to, also ask Emma and discuss broadly?
No, just for providing some insight into the constant phase element. So, yeah, I agree. Constant phase element right now, it's commonly abused. Let's just say that to fit whatever that's not a perfect semicircle, but rather a depressed one. But its original derivation comes from if there's any inhomogeneous surface, say there's a distribution of RC circuit. It could be a distribution of resistance, the distribution of capacitance, but rather like it basically like if the surface is not exactly the same, you will have a small distribution that's spread out, and that will cause like your RC circuit having also distribution time constant distributed semicircle. And when you overlap those semicircles together, you will often see that this is the depressed semicircle comes from the overlap of the distribution of RC circuit. Yeah, if you see the constant phase element equation over there, there's like a power of n to the imaginary j and omega. With the, if you, in the future, if you start to use any sort of commercial package for fitting and use like CPE for your fitting, and if you just keep in mind that if n, the result of fitting parameter n is closer to 1, that means that you're closer to a just like a pure capacitance. Whereas if n is like lower, like down to probably around 0.5 is what we typically you'll see. That means you have a pretty like inhomogeneous surface. It could be a surface or a homogeneous RC process. It could be like anything, honestly. Like, but that's why people are starting a bit abusing that and kind of don't give it like a really good explanation of what's going on. They just fit it and that's it. So yeah, be careful when you use it in the future. It has meaning, and it just people tend to forget or ignore what it actually implies. It actually n2 is 0.5. It's like if n2 is 0, it's just a resistor.
It's an RC circuit then, no? Oh yeah, no. Yes, okay.
0.5 is particularly people see if like a really mess up like a distributed circuit.
Mm-hmm.
Yeah.
Great, thank you so much, Alan. I still remember the first talk that I learned about EIS was yours when I first entered the group.
Oh no, please don't. I spend too much time on EIS.
Yeah, if you ever want to do some really high frequency stuff, talk to Alan.
Does anyone has any questions or comments for Emma?
I had a question. I don't know how much time we have, but I was wondering how you relate Fick's second law to like current and voltage.
So I'm pretty sure I myself only briefly reviewed the derivation because it was several pages. Basically, you understand the diffusion of the reactant to the surface, and so that's what's limiting it. And so the reactant in this case is your lithium ion, and you can kind of equate lithium ions to electrons passed in terms of current, if that helps, as well as like chemical potential to potential.
Okay, gotcha.
To add on to that, Fick's second law is usually purely concentration, like driven diffusion. If you're applying a applied bias across say point A to point B, you also have to consider like the drop in potential, electric potential, and that will affect the electrochemical potential of say lithium ion. And now you have to consider also how the electrical potential is distributed across that media you're talking about. That's a really complicated PDE to solve. But yeah.
Thanks, Alan.
I think we have a time for one more question. If anyone has urgent question. If not, feel free to leave some question for Emma if you have on the Slack. Thank you again, Emma. I'm gonna stop recording.